please take a moment to read this question before we start talking about it together. Now, this question's interesting. It is a bunch of physics students building an electricity distribution system. My suggestion to the students would be actually putting a transformer in here to step up that voltage as it goes through the lines. They haven't done so, so I imagine we're going to have some significant losses here. We've got a step-down transformer on the other side, so as we go from the primary to the secondary side, the voltage will be stepped down. As a result, the current will go up. Notice too, we also have two resistances, so that's for each of these lines. So that tells us the total resistance is 4.0 ohms. So I might keep that for later. So we've looked at this question. Notice we've got ammeter and voltmeter on this side, and we've got a voltmeter and ammeter on this side here. So let's look at what the question's asking us. They've told us the ratio of the turns here. That was in the diagram, but it's also underlined here as 5:1. That's how we knew it was a step-down transformer. We're told that it's an ideal transformer, and we know that when we do calculations, we're assuming that unless we're told a particular efficiency rating, but I've never seen that in a past question. It asks us to actually find some values. So we're told the current through the ammeter is 0.50 amps. So we want to find A2, V1, and V2. I might just stick with this diagram here because I find it much easier to visualize things. So 0.50 amps in this one here. So that means if we do questions about this side of the circuit, everything on this side would have a current of 0.50 amps because it's all in series. So everything on the other side of the transformer, that's going to have a higher current because we said if it's a step-down transformer, voltage goes down but current will go up. We do actually need the other side of this. Reason being, we don't have any information about the voltage yet. We know that the supply voltage here, this is V supply, and the voltage that would be measured by this voltmeter here, that would be V load. Now, the load is actually this globe over here, but we do need the voltage that makes it to that transformer on the other side. So that's going to be the load voltage here. You might just prefer to call that V1. But like in the other examples, we had a house or something there, so we'll call that V load or V1. I don't mind what you call it. So that means we need to find V drop. And in order to do that, well, we know the resistance is that 4 ohms, and we know the current. So this isn't too bad, actually. V drop is going to be current times resistance. Maybe I'll do it here. So V drop equals I line R line. The current in the line was 0.50 amps. The resistance in the line was 4.0 ohms. So we're going to have 2.0 volts. So what does that mean? It means V drop is 2.0 volts. So that means 12 volts is supplied, 2 volts is dropped here. So that means 10 volts is going to make it to V1. So V load is going to be 10 volts, which was V1. So let's put 10 volts in here. Oh, isn't that nice when they provide us the unit? Okay, so we know that this is a 5:1 transformer and the voltage is going down. And it's going from 5:1, so the voltage is going to be divided by 5. So that means V2 is going to be V1 over 5. And that's nice. It means it's just going to be 2.026 volts. Now the current, not divided by 5, it's actually going to be times by 5. So the current, I2, equals I1 times 5. I wish I'd written 5I1. So 0.50 times 5 is going to be 2.5 amps. It's really nice being able to use ratios with this. You could have, of course, used the V1 over V2 equals, we don't have N1 and N2 directly, but we could replace that with 5 over 1 because we know that's what the ratio is. And you could use I2 over I1 here. So if you prefer a formulaic approach with this, that's fine. I just find ratios are a bit quicker and easier for this style of question. Okay, so let's note down everything that we calculated. We found that V2 was equal to 2.0 volts. And A2, did we calculate that in the end? Yes, we did. It was 2.5 amps. So, now we're asked, what would the power be? What would be the power delivered at each of the points below? The output of the 12-volt RMS power supply, input to the primary coil of the transformer, and what's actually gotten at the globe. So I find it really useful to look at this diagram when I'm doing this. Okay, what colour haven't I used? So P supplied, that's going to be the supply voltage times the current. That's the current through this entire part of the circuit here, through the transmission lines, into the primary side of the coil, back through the transmission lines, and to that AC source again. It's jiggling in the lines. So I could put I line here. Okay, so that's going to be 12 volts RMS good. We needed an RMS value here. And the current in the line was given, that was that 0.50. So we're going to have 6.0 watts here. The input to the primary coil of the transformer. Okay, so if we want to find V1, oh, we already had V1, and we have the current. Oh, yes, good. So we have the current that is through the primary side of the coil, and we knew the voltage drop. Sorry, the voltage at that load was 10 volts because 12 volts was supplied to the left-hand side of the circuit. 2 volts was lost in V drop, and V load was 10 volts. So that means the power that actually gets there, P load, is V load times I line. Okay, you can already tell I need a little more room. Line. Okay, so 10 times 0.5, so we're going to get 5.0 watts. Oh, that's rubbish. We had 6 volts supplied, 1 whole watt has been lost. That's alright. 5.0. Okay, so the big thing about this, 5 watts is on the primary side of the transformer. That was P load, which also equals P1, the primary side. We know with transformers, the power in the primary side has got to equal the power in the secondary side. So that means, because there's no resistance in the lines in this side of the circuit here, that means that's also going to equal the power of the globe, because all of the power supplied to that circuit that's connected to the globe has got to be used by that globe. There's nowhere else for that power to be used. So that's a really nice question, testing our ability to know that the power on each side of the transformer is constant. The 12-volt RMS AC power supply is replaced by a 12-volt battery. Now, when they're saying a 12-volt battery, they mean a 12-volt constant DC. Batteries can't supply a variable voltage. Well, it does vary a little with time as the battery loses energy, but for the purposes of what we're doing, it's constant DC. What will be observed in the globe shown in Figure 8? Explain this observation in terms of the operation of a transformer. So there's a few things we need to mention here. When this circuit is turned on, initially it will work for a very brief moment in time. That's because we're going to have a changing current going from 0 getting to its maximum current in a very short time period, milliseconds. That changing current means that there'll be a changing magnetic field on the primary side, meaning the secondary side of the transformer is experiencing a changing flux, meaning there's an induced EMF and current. Once it's been on for some time though, those changes are no longer occurring. Everything's going to be constant, unchanging, very boring, and it will no longer operate. So we need to hit all of those points here. Okay, I thought it was recording then, but here we go. So, like we were saying before, the globe will momentarily turn on when the battery is first connected. After some time has passed though, it goes off. So the globe will no longer be able to light. Now we need to talk about why, and they've specifically told us to link it to a transformer. It's pretty generous. That should be something that you could just pick up from the question here. So we need to talk about why the transformer doesn't work. So the transformer requires the alternating, i.e. changing, current. We need to talk about the fact that it's in the primary side. And we said to produce the changing B field. This results in a changing flux in secondary side of transformer. This produces EMF and current. Okay, I think we've hit pretty much everything that we can hit there. 3 marks. Talked about what the globe will do, talked about what the transformer requires and what that will do. Let's check how we went. Okay, 37% of people this year got 0 for this. So it says the globe will not illuminate, in brackets, or the globe will momentarily, as the DC battery is connected. Great, we've hit that. Transformer requires a change in current in the primary to produce the magnetic field that threads the secondary. Oh, I like the way they use threads. I might use that next time. The resulting change in flux in the secondary produces a voltage. Some students, now this is a huge thing, so please don't do this. Some students just directly word vomited stuff about transformers or talking about reducing power loss in transmission lines here. You need to really make sure you're addressing the question specifically. I've harped on about that before, so I'm not going to keep going on about it, but please, you can't just information dump from your note sheet. Okay, this is a really interesting question. They've got a diesel-powered portable DC generator and it's used to power lights on a light tower in an isolated football ground. Now this is the interesting bit. The generator produces a constant 500 volts DC. So this is not like the generator questions where if we had voltage and time and we had a bouncy graph here actually going to 0. It's not this. They're actually saying it's a constant voltage. They haven't provided us with additional details here, but there could be multiple axes of the armature. They could have capacitors within it or other things to smooth it out to an approximately constant amount here. They are sort of glossing over this in the question, but the main thing I want you to take away, they've specified that it's a constant 500 volts DC. Okay, so the generator is approximately 500 meters from the light tower. That information is not probably going to be required for the question. They're just trying to signify that really long power lines have to have a resistance. They've also specified that each of the transmission lines has a resistance of 5 ohms. So that means our total is going to be 10 ohms, 10.0. Ignore the resistance of other connecting wires. That's really typical of this style of question. Okay, there's the diagram. With the lights on, the generator has an output of 20.0 amps. So what is the power output of the generator? Let's also do V supply equals, what was it, 500 volts DC? And we're just going to remember this is DC. So power equals, let's actually put the subscripts on. Power supplied equals V supplied I line. Or you could also say I supplied. The current that's supplied to the circuit is the current that will be within the lines. Supplied voltage was 500. Current in the lines was 20.0. Yeah, I'm getting my calculator out. Don't judge me. I'm on holidays. And I'd also do it if I wasn't on holidays. 500 times 20. Okay, so sig fig wise, we only want 3. So 1.0 by 10 to the 24. 00, sorry. Cool. Okay. Oh, I've just realised in the question, they've quoted this to the incorrect number of sig figs. Oh well. We're better. Okay, what is the total power loss in the transmission lines? So, we want to find P loss. A recommended way to find it would be I squared, so I line squared on R. Reason being, we already have the current within the lines, and we have the resistance. We don't currently, know the voltage drop across the lines. We could figure that out using V equals IR, but then we just have to substitute that into a power formula anyway. So, they've said total power loss because they're saying use that total value of the resistance here. So, P loss equals I line squared times R. Should have said R line before. Okay, current in the line was 20, and we've got to square it, nearly didn't. Resistance in the lines was 10. Okay, so 4,000 question mark? Look at me. Okay, 3 sig figs, so let's do 4.00 by 10 to the, we need 3, because it was 4,000. Okay, let's just pause and look at the stats on these questions here and talk about some common errors. Okay, so this question was generally well done. It does talk about assuming the resistance is only 10 ohms, but there is a resistance associated with the lights that I assume that we're going to be looking at later. So we can't actually use I squared R or V squared on R because we don't know the total resistance of this circuit. We know the resistance in the lines, but we don't know the resistance in the lights yet, which is probably going to come up a little bit later. So we had to use VI here. Now, question 10, you may notice, was significantly more worse off, and it says a substantial number of students only worked with the loss in one line. So putting in the total resistance there is just a helpful visual reminder of that. Some of them also tried to add the resistors in parallel, but as we spoke about, this is a series circuit, so we just directly add those two resistances together. Another common thing that you'll see is people using the incorrect voltage, but apparently it wasn't statistically significant enough that it turned up in this particular year. Okay, I think we're doing well. So, what is the voltage / potential difference across the terminals P, Q of the light tower? So this is V load. So there's a few ways we could go about this. I would probably find out what V drop or V loss is, and then we could use V load is going to be V supply minus V drop. Actually, I think that's my preferred method. So V drop we can calculate. We know I line and we know R line, and then we'll pop it in there. Great, we've got a plan of attack. So V drop is going to be I line, R line. The current in the lines was 20. Resistance of the lines was a total of 10. So we're going to have 200 volts. V load is going to be V supply minus V drop. Oh, this is woeful. V supply was 500, whereas V drop was a whole 200. So only 300 volts actually gets there. That's really awful. What mistakes did students make with this question? Some students only determined the voltage drop across the transmission lines. You could have also done it using a power method, but I think this was the most efficient. So a lot of students stopped here. So it's really important, this little scaffolding, giving yourself an idea of what you're doing rather than just doing V equals IR, making it really clear you're finding the drop and reminding yourself of this. We actually wrote that down in our plan of attack before, and I think that would have helped us avoid making that error. Okay, oh, we didn't actually, that's better. Okay, the players find the lights are too dim. They call an electrician. She suggests the following. Retain the diesel motor, but replace the DC generator with an AC alternator, producing 500 volts RMS. That's going to be great because we can use transformers to originally step up the voltage, which will step down the current, and then we can step it back down, and therefore the current go back up. So the lights can have the required voltage and current, and it means we're going to reduce power losses. We want to insert a 1 to 10 step-up transformer between the alternator and the power lines, and a 10 to 1 step-down transformer between the power lines and the light tower. So step up here, good, step down here, that's what we wanted. This was step up, this was step down. Remember, that's always in reference to the voltage or the number of turns. Current is inverse. The transformers can be considered ideal. Here's the arrangement, blah. Okay, the lights are on. That's good to know. The resistance of each wire in the transmission lines is still 5 ohms. Ignore the resistance of other connecting wires. The output of the alternator is 20 amps A RMS. So V supply was 500 volts, and I'm just going to put RMS, and I supply, which is also equal to the current in the lines. Well, actually, no, it's not now because we've got a transformer, so not true. So not true transformer. Okay, I'm glad I made that error but then corrected it. So I supply 20.0 amps RMS. Great, we've got RMS values so we can do calculation, power calculations with complete confidence. Okay, so we're asked what is the RMS voltage or potential difference that will now be input to the transmission lines at point XY. So we're asked for this voltage here. Okay, so these lines and within the transformer there's going to be no resistance, so no voltage drop or losses or power losses here. So that means we can do a straight transforming situation. So this is a 1 to 10 transformer. So that means the voltage is going to be multiplied by 10, the current is going to be divided by 10. So if the supplied voltage is 5,000 volts, that means the voltage here is going to be, sorry, I think I misspoke. Supplied voltage was 500, I think I might have said 5,000. That's because the voltage on the secondary side of the transformer is going to be 5,000 VRMS. They don't ask it yet, but the current on this side is going to be divided by 10, so it's going to be 2.0 amps RMS. So I'm just going to make a note of that for later. Okay. So, just checking we've read the question. RMS voltage potential difference now be the input to the transmission lines points at XY. I feel like we've been given a lot of room for this, or maybe that's my error. Whatever. So we need to make a note. We've basically answered the question, but we do need to mention it. So V supply equaled 500 volts RMS. It's a 1 to 10 transformer. Therefore, I'm going to do XY, just so I can have something to label it as. VXY is going to be 10 times V supply equals 5,000 volts. Let's chuck 5,000 in there. I think we've overworked that question. You don't need to put this and then also have that there. So just out of interest for this question, some students try to use Ohm's law or P equals VI, incorrectly substituting in values. Some were trying to find an RMS value even though it was already there. So this is a straightforward question, but easy to make errors with it if you're not clued into some of those tricks that are going on there. Okay, the primary of the step-down transformer has 4,800 turns. How many turns are in the secondary winding? This is a 1-mark question. Now, I've had to re-record because I did the exact thing I was just harping on about. I didn't read the question. I did the calculation for a step-up transformer, but they've specifically said step-down transformer. So that means they're actually talking about the second transformer here, this one for this question. So we're told that N1, this is for the step-down, so N1 is 4,800 turns. So that means because N1 to N2 is, if it's stepped down, then it's 10 to 1. That means N2 has got to be this value divided by 10, because we're stepping down the number of coils, stepping down the voltage. So that's going to be no unit because we're just talking about the number of turns. Power loss in the transmission lines were asked. Okay, so to know this, a couple of things. I've made a bit of a butchered mess of our diagram. The supplied voltage to the transmission lines is this value here. That is the voltage that is at the start of the transmission line. So that's our new value of V supply for this question here. It can't be the voltage that's directly provided by that alternator because it has been transformed into a larger value. And that's the whole point of using the transformer there. So that's our new V supply. Before we calculated what that current was, so we do need to reference that in our working out because we haven't formally done that yet. That was just sort of our plan of attack. And we know the total resistance is 10 ohms here. So let's go ahead and formalize that. Okay, so step up transformer. I1 equals 20 amps, therefore I2 equals 2.0 amps. I think that would be sufficient. So P loss equals I line squared R line. So 2.0 squared, and the total resistance was that 10 ohms. So that's going to be 400. I'm just going to leave it as 400 because that 2 amps could have been written as 2.00. Oh, wait. 4 times 10. That's 40. Never mind. There we go. So it's 2 sig figs now, so we're all good. Cool. Could have also figured out V loss and then substituted that into a power formula, but it's more work than you need to do. Okay, what will be the voltage at the output of the step-down transformer? This one's a little more involved. So the supplied voltage here is 5,000 volts. We don't know what the dropped voltage is. So that's not too bad. We can find that out. So V drop would be I line times R. Current in the line we're told is 2.0 amps. The resistance is 10 ohms. So that's not too bad. We've got we can only do 2 sig figs. 20 volts. Now, I'd like you to just mentally compare that. We have 20 volts dropped versus in the previous question, oh, sorry, I should compare 20 volts dropped, whereas we had a supply of 5,000 volts. That percentage drop is so much smaller than the questions that we had without transformers. So thank you very much, transformers. So that means the voltage that's supplied to here is going to be 5,000 minus 20. So we'll call that V1 because we're going to use that in a transformer circumstance soon. So we'll call this V1, this V2 for this question. So we're going to have 4980 volts. That's a lot nicer. Okay, so we want to find out what V2 is. Because it's a step-down transformer, we're going to have to divide it by 10. So it's going to be 498 volts. So let's actually do that calculation a bit more formally in our working out. Okay, how do people do in this question? Only 35% of students this year got 3 volts. So, they did it the same way. So 20 volts was lost. They found the voltage input to the step-down transformer, and then the voltage on the secondary side. I like that approach. You could have also found the power losses. So we knew that 5,000 times 2 amps would have been 10,000 watts provided to the transmission line circuit. Then you could have figured out, like we did previously, we knew that 40 watts was dropped. So you could have used a power approach there. Some people tried to do some strange things with RMS values, but yeah, didn't have to. Everything was provided with RMS in this circuit. Now, I've realised there aren't actually any explanation style questions in any of these examples. So what I'm going to direct you to is looking at some of the question bank questions with regards to transformers there, and it has some examples of how to actually word some of the answers to some of those questions. I think that will be really valuable to you. So along with doing these transformers questions, 8C I think it is in Ed Rollo, I really encourage you to look at some of those questions because explanation style questions are always out there. Okay, I'm going to edit this and see how many minutes I can take off because it's going to be 34 by the time I finish. Let's see how I do.